What does albedo mean? What's the difference between a texture, shader, and a material? What does the normal map actually do? I'm on a mission to explain every 3D concept in the simplest way possible. In this video, we'll cover the basics of 3D materials. What materials are, how common shaders work under the hood, the PBR workflow, procedural textures, and normal bump and displacement maps. Let's jump into it. What is a material? Well, in short, it's what gives your 3D models color and texture. You can think of a material as a list of properties telling your 3D program how your 3D model should look. There's countless ways of creating materials by changing values in a menu, making it with nodes, coding it from scratch, or by using external software specialized for materials like Substance Designer. There are three words that often come up when working with materials: textures, shaders, and of course, materials. But what do they mean and what are the differences? Textures are images like color maps or normal maps that are used in your material. And map is just a shortening for mapping. For example, the color map, which feeds colors into the shader. Shaders take those textures and decide how they look on screen. For example, an emission shader makes something glow, while a glossy shader controls how shiny or rough the surface is. Materials, on the other hand, contain the textures and shaders used to create the final look. Let's look at some of the most used shaders in 3D. Diffuse shader. A diffuse shader takes a color input and calculates how that color looks under lighting. Think of it like pointing a flashlight at a sphere, and the diffuse shader decides which parts should be bright and which parts should be dark. If you plug in a color texture, it's usually an albedo map. An albedo means the raw color of a surface with no lighting applied. Imagine looking at a face with no lighting or shadows, just pure color. It would kinda look like this. If you plug this into a diffuse shader, we'll get light and shadows. Shaders affect how light bounces off the surface, and when we say bounce, it just means how the light goes from its source, hits the surface, and bounces off. Like mentioned earlier, we have the glossy shader, which simulates smooth reflective surfaces like glass, metal, or plastic. Glossy shaders usually have a value called roughness or glossiness, which controls how sharp or blurry the reflection is. Higher roughness means blurrier reflections, while if the shader uses glossiness instead, the values flip around, so then higher glossiness means sharper reflections. This means that if you connect a glossiness map into a roughness slot, you have to invert the values to make them correct. And then we have the refraction shader, which is used for transparent materials like glass, water, and crystals. And instead of bouncing off, light goes through the surface. And a value called IOR, or index of refraction, controls how much the light bends inside. You can look up real-world IOR values on Google, and if you use these in your shader, the light will bend more realistically. For example, clear water has an IOR value of 1.33. Then we have the metallic shader, which controls how metallic a surface is. An interesting thing about metals, they color the reflected light. For example, this white light hitting a pink metallic sphere bounces off as pink light, whereas on plastic surfaces, it stays white. Specular shader simulates the bright highlight that appears when light hits a surface directly. Opacity can make parts of the mesh see-through by changing a value, or plugging in an alpha map. This is useful for 3D objects like leaves, where instead of modeling the full leaf, you can just apply an image of a leaf on a face and use opacity to make the outside of the leaf transparent. Emission emits the color input as light. The higher the emission, the stronger the light it emits. Subsurface scattering, or SSS for short, simulates light going through the skin, which helps skin and wax look more realistic. If you hold your finger up in front of a light, you'll see the light scattering inside your finger. This is what subsurface scattering simulates. Coating or clear coat. If you're into rendering cars, this one is essential. Imagine if you paint a car, you first apply the base paint, and then you apply a coating, giving you a nice glossy finish. Clear coat basically simulates this thin layer on top. It does not affect color, only reflections. And then there's something called anisotropy, which controls how a light stretches in a specific direction. This is most often used on brushed metal, hair, and fabrics. These shaders are often mixed and combined to create materials. However, you might notice that this is a lot of shaders to keep track of, and it feels a little bit overwhelming. It did that for me at least. Well, the nice thing is that most modern 3D software uses a standardized system called the PBR workflow, short for physically based rendering. This helps keep materials both photorealistic and consistent. You can build a PBR shader manually by combining multiple shaders, but most 3D software already includes a dedicated PBR shader with everything you need. For example, Blender has the principled BSDF shader, and texturing tools like Substance Painter also follow the PBR workflow. Now that we've covered how shaders behave, let's look at what actually feeds into them. And hey, if you're enjoying this video so far, consider subscribing. It really helps. Shaders can take all kinds of inputs, values, colors, images, videos, and even procedural textures. And procedural textures are patterns, noises, or any texture generated directly in the 3D software. They're great for things like adding bumps, subtle imperfections, or stylistic patterns. For example, gradient textures, which are used for generating, well, gradients. I often plug these into color ramps to create some nice looking gradient colors. Then we have Voronoi or cellular textures, which creates organic patterns. Great for things like stones or skin pores. And in Blender, for example, we have a brick texture, which generates, well, bricks. What makes procedural textures like these great is that you can scale, rotate, and move them freely without running out of resolution. And that's one way of adding details to a material. But no matter what procedural texture you plug in, it might still feel flat. However, there's a few ways you can add depth to your 3D material without actually modeling anything. Some 3D programs have a displacement output, which can make the surface be pushed in or outwards. Usually, we use something called a height map or displacement map to control the displacement. That's a black and white image where the brighter something is, the more the surface gets pushed out. For example, if we use this brick texture as a height map, it will displace the model like bricks. And this can be applied to any model. But the quality of displacement depends on the number of polygons on the mesh, so full displacement can be heavy. And that's where normal maps come in. You've probably seen those blue and pinkish textures, and plugged into a normal slot, they make the surface look more detailed than it actually is. And the reason for this is that the normal map, well, maps the normals. If you watched the first video of this series, you might remember normals as arrows pointing out from faces to indicate the direction the face is pointing. Well, this direction can be mapped and changed, which will change how light and a number of features interacts with the material. Usually, a 3D face points in just a single direction. However, if we add a normal map, we can define the direction of the normal all the way down to the exact pixel. In practice, normal maps add a lot of detail without having to add any polygons to the model. We also have bump maps, which, like height maps, are black and white images where brightness represents height. Shaders generate normals based on this, creating a similar effect as normal maps. However, compared to bump maps, normal maps store the actual direction of the surface normals, not just the height. And that's why they capture more precise detail and lighting information than a bump map. And the data is encoded into the map's colors. So, since a bump map is just black and white, it only represents height. While the normal map encodes the surface normals X, Y, and Z components into the red, green, and blue channel of the texture map. Normal maps usually look blue because most normals point outwards, and the blue channel stores that outward direction. The red and green channels control side-to-side variation, which there's usually less of. And that's it for this video. I'm working on the next one right now, covering surfaces, UV mapping, baking, and a few more concepts I didn't have space for in this video. So stay tuned for that, and thanks for watching. See you next time.